Okay, so the oriented Plateau problem. So what is this? So first of all, the classical Plateau problem, which is, as often in mathematics, not named after the first person actually raising the problem, because apparently the person actually raising the problem is Lagrange. Anyway, nowadays in the literature, the problem is named after Plateau, who was a Belgian physicist at the beginning of the 19th century. And he was studying the following problem motivated by physical phenomena. So you have, say, a curve gamma, which is sitting in R3. And you are looking at the surface. Let me put quotation marks, sigma, which bounds gamma and minimizes the surface area. Okay, and probably I should also put quotation marks on what it means here, bounds. So why am I putting actually quotation marks over here? Because depending on what you understand as a surface, and depending on your concept of what it means for sigma to bound gamma, you might actually get different answers. And these different answers might not necessarily be, wrong. It depends also on what kind of problem you want to model. So for instance, if you're really interested in the original physical problem of Plateau, then you might discover that if you minimize among the category of smooth surfaces, you're not actually capturing all physical phenomena that you wanted to capture. Anyway, so there are various ways of defining what it means to be a surface in general, what it means to bound gamma. But anyway, in this talk, I'm always going to assume that sigma is oriented. So that is going to be one key assumption, and that's why I've actually given in the title the oriented Plateau problem. And gamma, if sigma is smooth, then gamma is the boundary of sigma in the usual differential topological meaning. So let me just write here in the usual sense of smooth submanifolds. Okay, and although the original question was posed for two-dimensional surfaces in R3, in this talk I'm going to consider a much more general situation. So instead of having a curve gamma, I will have a submanifold gamma sitting in some Riemannian manifold M. So gamma in M is an M-dimensional submanifold, which is a boundary actually M minus 1, sorry. Okay, and then I'm looking for surfaces sigma in M. So M-dimensional surfaces oriented which minimize the M-dimensional volume among all sigmas or sigma prime, so that the boundary of sigma prime is equal to gamma and sigma prime is sitting inside M. Okay, so, sorry?
Do you care about the dimension of the manifold?
Not that much. So the dimension of the ambient manifold, maybe I'm going to define. So the dimension of M is some M plus N. And then if N is equal to 1, I'm looking at hypersurfaces. If N is larger, I'm actually looking at what I will call the higher codimension situation. And typically in this talk, I'm actually considering the higher codimension situation, which means just N is equal to and larger. Okay? And on purpose, I'm actually here, I'm just saying submanifold, because on the data, I will assume smoothness. I mean, if you're interested in precise smoothness that I'm going to assume, it's at least 4 times differentiable. But on sigma, I'm not assuming any smoothness for the moment. I mean, this sigma is just a surface. I mean, somehow I could maybe here just say some oriented generalized M surface, which I will make precise in a couple of seconds. Okay, so of course the first thing that you might bother as a mathematician is whether such a surface exists. For instance, if you try to minimize among all smooth surfaces, you might actually end up in obstructions in proving that such a surface exists. Maybe, and we will see that this is the case, in fact such a surface does not exist because the minimizer of the area is bound to introduce some singularities. Okay, so in which sense you can actually understand a notion of generalized surface which gives you a theorem of existence, at least at the beginning. So I will consider the following framework. So the framework of integer rectifiable currents, which I will define in a second, which is due to Federer and Fleming. In a foundational paper in the 60s for general codimension, but which in fact was already introduced by the Giorgi earlier in the 50s in the case of hypersurfaces. Okay, so first of all, let me explain what I mean by a current. Okay, so by a current I mean simply a linear map on the space of forms. So the idea is the following: if sigma is an oriented surface, I can integrate over this oriented surface any form omega, which is smooth, and I can think of sigma as something which is taking a smooth differential form and splitting a number, right? So I can think about integrating the form omega over the surface sigma as a linear map on the space of forms. Okay, so if I take this point of view, relating, so the fact that gamma here is the boundary of sigma can be simply defined by using Stokes' theorem, right? So this is for an oriented M surface. In general, for a current, I'll just have the action as a linear functional, and I don't know if this action is actually given by the integration over a surface or not. It might not be given by that. And now, in general, if this L is a current, the boundary of L can be defined on a surface omega, on a form omega, as simply the evaluation of L on the differential of omega. Okay, and of course, Stokes' theorem just tells you that this definition is compatible with the usual definition that I take when sigma is a smooth surface with a smooth boundary. Okay, so this is what the boundary means. Okay, in the same vein, I can actually define what the M volume of a surface sigma is by simply observing the following. If I am integrating a form omega with modulus 1, modulus I would have to define somehow, but you can introduce an appropriate notion of modulus of a form, a norm if you want, on differential forms. If I'm integrating over a surface sigma a form of modulus 1, then an obvious inequality is that the modulus of the integral is less or equal than the area of sigma. So I have an inequality of the following form. In the smooth case. And I can somehow define this m-dimensional volume for smooth surfaces as the supremum, or if you want, as the optimal constant, which gives me this inequality. And of course, you see that this is independent of introducing somehow a notion of what is measuring the surface. Actually, it just requires a way of measuring the length of a differential form, which if you are in a Riemannian manifold is actually well defined. So in this way, I can in general define what is the mass of a current L simply by taking the supremum of the action of L over all forms omega which have modulus less or equal than 1. Okay, and this defines a notion of total area of your, or total volume of your current. And once I actually give you these definitions, it's rather easy to check by classical functional analysis that there's always a minimizer in this context. So this is a simple exercise in functional analysis. There is always a minimizer or a mass minimizing current. Now, on the other hand, there is a problem with this, and the problem is that if I give you half of a surface, okay, I can define this half of a surface as a current. Okay, so this is a very well defined, so sigma smooth, and if I just integrate over sigma my form omega and divide by 1/2, this is a very well defined current. And you might say, okay, maybe I want it, maybe I don't want it. Even if I want this, you might actually ask, if I give you a honest curve in R3 or in R4, and I actually take the minimizer in this context, am I going to pick up coefficients which are not integer? And in higher codimensions, so if you are in codimension higher than 1, this might actually happen. So in this framework, there is a first example which is due to L.C. Young. And later there are simpler proofs by Frank Morgan and Brian White. So there exists a smooth curve gamma in the 4-dimensional space such that the corresponding mass minimizing current takes non-integer multiplicities. So in other words, it's not a classical surface. And okay, so this being the case, if you are interested in some classical I mean, if you are interested in kind of more classical solutions, then you would naturally wonder whether you can introduce a subclass of the space of currents in which I'm imposing actually that this coefficients that I'm taking is not 1/2. On the other hand, I want a subclass of currents which is closed in the whole space of currents in such a way that by the direct methods of the calculus of variations, I can still find a minimizer. This time, it will be a minimizer which is not going to exist because of a single exercise in functional analysis, because when I am restricting the nature of the coefficients, I'm actually breaking kind of the linearity of the space, right? So if I only allow you to use integer coefficients to construct your surfaces, and then I kind of close in some weak topology, then I'm not anymore a linear space, and then the existence of a minimizer is not anymore a simple exercise in functional analysis using, for instance, I don't know, Bourbakis theorem or whatever, Alaoglu's theorem, so compactness under weak convergence. Nonetheless, this is possible, and when you actually try to do this, you land into the so-called integer rectifiable currents. Okay, so there are two ways that you can think about integer rectifiable currents, and I'm not going to give you the precise definition anyway. So one way it would be just to say, okay, so let me just think about smooth oriented submanifolds with integer coefficients, and in some sense close it in the space of currents, so to get a nice set on which I can apply direct methods of the calculus of variations. So this is one way you could do it. The other way you could do it is to give a kind of direct definition, and the direct definition is kind of more elaborate. So essentially, so a current T is integer rectifiable if there exists countably many C1 surfaces, sigma I, countably many subsets which are closed, and countably many integer coefficients such that the action of my current T on a form omega is equal to the series which I get by integrating over these classical pieces and multiplying by my integer coefficients. Okay, so you just give me a countable collection of C1, I mean of closed pieces of C1 surfaces, and then you give me just arbitrary integer coefficients, and then I just build up the series. And if, I mean, of course, you have to put some convergence condition. One typical convergence condition that you can put is that the sum of the moduli of the Ki times the volume of the Ci is less than infinity, so that this series is absolutely converging. Okay, so if that, I mean, if you have such a representation, that is an area, that is an integer rectifiable current. And it's a very non-trivial theorem of Federer and Fleming that these 2 points of view are equivalent. Now, if you're more used to kind of analysis and PDEs, you can think about the space of integer rectifiable currents as a nonlinear version of the space W12. If you think about the area functional as a nonlinear version of the Dirichlet energy. So you have the Dirichlet energy, you would like to minimize them into the space of smooth functions. Well, you allot the space of smooth functions to general distributions, but then actually if you close the C infinity functions relative to the energy, you find W12. Okay, and of course the density of C infinity functions in W12, if you define W12 in some other abstract way, is a much simpler question nowadays, but I mean, like long ago, it was a non-trivial question. Okay, so now once you actually have this theory by Federer and Fleming gives you a minimizer, which at least up to a certain measure theoretic sense is really a sum of integer multiples of classical surfaces. Okay? So the only thing which is disturbing is that I'm not really taking the classical surfaces, I'm actually taking C1 pieces, and I mean closed pieces, and these closed pieces might be actually very scattered. For instance, an integer rectifiable current might have actually wedges, might make angles, right? So if I take the boundary of a cube, well, the boundary of a cube is a very nice integer rectifiable current, but it has edge singularities, right? So where I have the edges of the cube. So by using this theorem, you have actually existence of minimizers. So this is Federer and Fleming. And what I want to bother today is actually their regularity. So are they more regular than you start with your definition and with your scattered pieces? So for instance, can you allow, I mean, do you allow angles? Do you allow cusps? Do you allow tips? Or actually this sort of objects? And let me just start right away by telling you that in general they are not regular. So not in general. They actually have to be singular in a lot of situations, and then you would naturally ask how large is the singular set of the minimizer. And let me also split this question about regularity and how large is the singular set into two sub-questions. So first of all, you might actually inquire about regularity and singularity of the minimizer when you are far away from the boundary. And this I will call interior regularity. But then you might also wonder what happens to a point which is sitting on the boundary, and whether your minimizer is regular over there. And of course, when I mean regular in a point which is outside of the, far away from the boundary, I just mean whether there is a neighborhood such that in this neighborhood your current is going to be a multiple of a nice smooth submanifold, a single piece. And when I'm actually at the boundary, I'm understanding regularity in the sense that in a neighborhood of this point, my current is going to be a nice submanifold with that boundary as a smooth submanifold. Okay, and this I will call boundary regularity. Okay, and so now, of course, you could ask, why do I bother about regularity? Well, it's very natural to bother about regularity if you want to address any kind of interesting geometric question that you have on these objects. So let me give you this toy question as a kind of guiding toy problem for understanding at a deeper level the structure of the minimizer. So this toy problem actually turned out, to my surprise, to be open since now. And one of the outcomes of my most recent research, which I'm going to present today, is that we can give an answer to this question. So, and this question was posed by Almgren. And the question by Almgren is, if your boundary gamma is connected, so is, I shouldn't say the minimizer because there are situations in which you have more than one minimizer, is any minimizer in the context of integer rectifiable currents also connected? Every, yes, sorry. Yeah, English is still a foreign language for me, sorry. Is every minimizer also connected? Okay, so first of all, a disclaimer. It was open when Almgren sort of posted it, and he could only solve the following particular situation. So he gave an answer which is yes, if your ambient manifold M is the Euclidean space. Okay? As a result of a if you just take all the things that you need to prove this corollary, it's going to be a more than 1,000 pages long proof. Okay? And together with 3 friends, so Guido de Philippis, Jonas, Hirsch, and Annalisa Massaccesi. By the way, this was essentially 1980. And this is 2018. So yes, for any Riemannian manifold.
Can you clarify what connected means? So the minimizer is some formal sum of
right.
sigma.
Exactly. So you could ask several. You could ask this question in several ways. So one way you could ask is whether you can define the support of the current, which is going to be a closed set. You can ask whether that closed set is connected. Okay. You can ask it actually slightly better. So you can take the regular subset. You can take the subset of regular points, of regular interior points. That gives you a nice submanifold as long as you don't bother what is happening at the singularities. And you can actually ask whether that piece is connected. And what I'm going actually to show you in a couple of seconds, since there are powerful enough regularity theories which tells you that the singular set is kind of small in a dimensional sense, the connectedness of the support and the connectedness of the regular set is the same. So at the end of the story, the answer is it is a regular connected submanifold, which might have singularities, but the singularities does not contribute to the boundary, and so I can just take them out, and then I have a regular connected submanifold whose boundary is going to be this guy. Okay? But we will see that the answer is slightly more refined than this. I mean, there are some subtleties. Okay, so I mean, this is just a disclaimer. This is a guiding principle because, okay, we have a proof of this, which is maybe not 1,000 pages long, but it's a 400 or something like that. So it's still, sorry.
That's as simple as, suppose you have a sum of two surfaces which intersect. So this we call connected.
No, if I have, okay, so if I have a sum of two surfaces that, it depends on how they intersect. So for instance, if you have a sum of two two-dimensional surfaces which intersect on a line, okay, that disconnects the regular set because the intersection is. If I have a sum of two surfaces which intersect at a point, the point is a singularity and doesn't disconnect the regular part. So the best answer that I can tell you is that the singularities are not disconnecting. I mean, it's a general connected closed set, and the singularities are not disconnecting actually the regular part. Okay? So in other words, there is a unique a smooth submanifold, and I can connect any point inside with a path which is passing through regular points, all of them. That's the best answer that I can give you. Okay, so the proof here is still pretty complicated, and maybe there is a slick way of proving this, which is just a couple of pages, and I don't know of. Okay, so it's a disclaimer. I'm just using it as a toy problem to motivate the regularity issue. Because in fact, what we are proving is a much deeper regularity theorem, and this comes out as a corollary of that regularity theorem. And this is just a guiding principle to tell you that, okay, the regularity theory is per se interesting because it gives geometric consequences. And without the regularity theory, it seems impossible even to tackle a very innocent question like this one. Okay? So now, before I go into the regularity question, let me just show you how simple the answer to this question is if you are regular, okay? So if I know that I have full regularity, if I know that my minimizer is really a smooth submanifold with that boundary, okay? So first of all, what I notice is that since the boundary is connected, right, by moving a ball around this boundary, I just discovered that there is at most one connected component of my minimizer which takes this boundary, okay? Now, the other piece, which belongs to the minimizer, must be completely disconnected. But if it is completely disconnected, I can just erase it, and I get a competitor which has less area. So obviously, the disconnected piece cannot be there, okay? So it's, so with regularity, so the answer is trivial. Okay, so therefore, let me just get to what is known nowadays about the regularity of the surface in question in at the boundary and at the interior. And let me distinguish two situations. So codimension 1 and higher codimension. And so let me first tackle the interior regularity. Okay, so in codimension 1, it's the cumulative work of several people. So I should credit certainly the Giorgi, then Fleming, Almgren, Simons, Federer, I think in this order, and then a few other people if you are interested in more refined results. But let me just stick to the question on how large the singular set could be. And then the answer is in an M dimensional minimizer, the interior singular set has dimension at most m-7. It's really tiny. In particular, you have to get to 7-dimensional surface to see the first singularity. And it's optimal. There is a classical example, which is due to Simons, of a 7-dimensional surface in R8, which has a point singularity. And the fact that this is a minimizer was proved by Bombieri, De Giorgi, and Giusti. Okay, and what happens actually at the boundary? At the boundary, the situation is even better. The boundary consists only of regular points. There can be no singularities at the boundary, so the singularities can only happen in the interior. And this is a work by Hard and Simon. So the boundary singular set is empty. Okay, so this is, of course, just telling you that that program can be run immediately if you are in codimension 1. That program can be run immediately because the singularity has codimension 7. The interior singularity has codimension 7. It's not going to disconnect anything, right? So as long as the interior singularity has codimension slightly less than 1, so m-1 minus epsilon would suffice not to disconnect the regular part. And then at the boundary, you're fully regular. So then you can answer to that question in full generality, no problem. Okay, so what is known in the interior? Okay, so in interior, so this is, and I will come back to this. It's a fundamental work of Almgren in codimension higher than 1. And this is exactly the work in which he posed that question over there. So the interior singular set has dimension at most m-2. So fantastic. Again, the singular set in the interior is not sort of disconnecting anything. And this is also optimal. And the optimality of this I will actually discuss in 5 minutes. So I'm not going to give you any reference for the moment. And what about the boundary? And now here comes actually the thing which is really not satisfying, at least up to now. So in this generality, in a general Riemannian manifold, for a general boundary in higher codimension, so if you give me a 4-dimensional manifold like S4, right, so the 4-dimensional sphere, and you pick up a curve inside, then up to now, the regularity theory tells you nothing at the boundary. So nothing means the singular set at the boundary might be the whole boundary for what is known up to now. Okay, so it's not actually completely true that it says nothing. So if you add some assumptions, then you actually do have boundary regularity. Okay, so let me tell you what is the thing which is really working in any codimension as compared to the Hart-Simon result, which anyway, it's also in the 1980. Okay, so the PhD thesis of Bill Allard in 1969 actually shows the following. So if gamma is in Rm plus n and is sitting at the boundary of a uniformly convex set, then there are no boundary singular points. Okay, so for instance, if you give me a curve in R4, and this curve is sitting on the unit sphere, which is a nice uniformly convex set, then the minimizer might have singularities in the interior, but doesn't have singularities around. And actually, sort of 1970s, this result was strengthened by Hard in the following sense. For a general boundary, if you give me the outermost point, or in other words, if you have a uniformly convex set which is passing through this boundary point and is acting as a barrier so that the boundary is all on one side, that then point is regular. Now, once you are, of course, in the Euclidean space, you can take the smallest ball, for instance, which actually contains your boundary curve, and that smallest ball must touch the curve at some points. And so R's result is actually telling you that in the Euclidean space, there's always at least some regular points. So let me just say the outermost points are regular. And what Almgren is actually doing in this is just saying if you are in the Euclidean space, the existence of one boundary regular point is enough to make a more sophisticated argument go through. So more sophisticated than this. So what you actually need, you need a sufficiently powerful regularity theory in the interior, which is telling you that the interior singular set is not disconnecting the surface. And then you need one singular boundary point which is regular, which of course comes with the neighborhood of regular points. So I mean, there's a small piece of the curve which is regular, or a small piece of the manifold which is regular at the boundary. Then you actually can prove that the answer to this question is yes. Okay, and what are we doing? What are we doing somehow in this paper over here? So in this paper over here, we're actually showing the following general theorem, which I could put over here. Okay, so what we actually prove is that the set of boundary singular points is meager. In your boundary gamma. So it's a closed set with empty interior. So which tells you, on the other hand, that the set of boundary regular points is actually an open dense set. And so there's always actually some of them in any situation. Of course, what I should have also remarked is this outermost point sort of argument, which works very well in the Euclidean space, is not going to work if you have, for instance, a closed manifold. Right? So you would need, I mean, for it to work, you would need a foliation of your manifold with convex surfaces, right? And I mean, if the manifold is closed, that's not going to exist. Okay, so far so good. I've told you all of this. Now, let me tell you exactly why, or let me give you a flavor why this thing is so complicated. Okay, so first of all, that result by Almgren over there, although it's optimal and it's sort of a fundamental landmark in the regularity theory, it has one disease. And the one disease is that, so Almgren's proof is almost 1,000 pages long. Actually, the original manuscript was 1,728 pages, but it was typewritten. So then with tech, you can actually kind of compress the pages. Okay, the fact that it's 1,000 pages long is not the only disease. I mean, the real problem is that nobody has really penetrated the entire proof. And so this was a stumbling block, and people could use it as a black box, but not sort of adapt the proof to other situations. Some portions actually of this proof has had a lot of impact in several other fields, I mean in PDEs and so on, but the full proof was certainly not understood. Okay, and so I've been working with, I had been working with Emanuele Spadaro on a simpler proof for quite a long time, and essentially around 2015 we have a shorter proof which is still following a lot of his ideas, but which also introduces some new ideas. And what I always thought, and what I always said in talks, is that these ideas would have actually allowed us to go further. And okay, so this boundary regularity theorem that I have over here is something where we can actually go further thanks to the ideas that we have introduced over there. Because at the end of his book, at the end of the 1,000 pages long proof, this question that he is posing about the connectedness is intimately related to the fact that he's not able to use his theory to prove the existence of some boundary regular points. Okay? Very good. So this paper that is actually not yet on the web, but it will be on the web soon, is building heavily on our 5 papers shorter proof of Almgren's theorem. Okay, and there are actually some other results in which we could go further, but I don't want to mention them now. Maybe in the other 2 lectures I will be able to mention them. Okay, so but now the first question that you might ask is, why is the proof so hard? Sorry? I think the current version is a couple of 100 pages, but we can certainly get much better. I mean, now that we are working at related problems, we start discovering that we can get better. I don't know, we can maybe get to 150, optimistically. I don't think we can go much below that. But okay, 150 is the size of somehow reasonable papers. Okay? So, I mean, one of the problems in here is not only that the proof is really long, is that it's very difficult to penetrate what he's doing. I mean, like some of the main theorems, some of really the main theorems which makes this thing work, have actually statements which go like 8 pages with 50 constants maybe inside. Okay, so there's nothing like that in our papers. I mean, even though our papers are long, the longest kind of building block of our proof is a theorem which can be stated in half a page anyway. Okay? So, and that, of course, makes it easier for other people to use it. Okay, so why is the proof so hard? And why is the interior case simpler? And then let me, I mean, this is going to take 5 minutes. The second one is going to take 5 minutes. And then let me give you one interesting computation. Okay, I will not be able to actually explain how the proof is going. In the other 2 lectures, I will try to explain some of the main ideas. But one thing that I can do is I can show you one interesting computation, which is just a calculus computation, and it has an effect on a very simple toy PDE problem. Okay? Okay, so first of all, you have to understand why the proof of Almgren is so complicated, you have to understand why, I mean, what kind of singularities you can see. Okay, and this is also showing you why the theorem is optimal. Okay, so first of all, there is a theorem by Federer, which is based on a classical computation in complex differential geometry by Wittinger, which tells you the following. So a holomorphic subvariety of Cn But in general, an holomorphic subvariety of a Keller manifold is always a minimizer. So in particular, if you take this guy in complex coordinates, so this very nice holomorphic curve, so this gives you a two-dimensional surface in R4 which has a singularity at the origin, right? And it's a branching singularity. Now, when you see something like this, why, as a PDE guy or as somebody in geometric analysis, you know that this is going to create a hell of a lot of troubles? The reason is the following. And when we're dealing with this kind of weakly defined objects, the regularity theory is always built on some epsilon regularity theorem. The epsilon regularity theorem is telling you if in average your surface looks flat, then actually in a smaller region it's going to be a classical surface. Okay? This is what actually literally works in codimension 1 and what was proved first by the Giorgi in that situation. Now, what is very problematic about this is that around 0, this looks very, very flat in average, because you can think about it as w to the 3/2. Okay, you have to choose a determination of the square root, but once you've chosen a determination of the square root, your tangents are actually very, very aligned to the horizontal plane. So you are in the usual kind of assumption of an epsilon regularity theorem without being regular. And not only, I mean, this is a kind of simple example. You can actually be much nastier. You can look at a curve like this. No, maybe this. Okay. So this is also an area minimizer, and if you attempt a Taylor expansion around the singularity, you will see something like this. Which means that not only the surface will be very flat. When the surface is flat, it tells you that the first order is kind of regular, right, in a C1 sense. But there is a whole hierarchy of Taylor expansions that you have to go through before finding your singularity. In other words, the singular behavior of the surface is a very high order perturbation of something smooth. And capturing this very high order perturbation is usually something very difficult. Okay. That's the first 5 minutes for why is the proof so hard. Why is the proof actually harder at the boundary? Okay, so this was a surprise to us as well. So Almgren's result actually was refined some 8 years later by Chang in the two-dimensional situation. So if M is equal to, the interior singularities are isolated. Okay? So actually, he didn't give a complete proof of this. I mean, if you read his manuscript, what he says is that, okay, so there is something that he needs from Almgren's paper, which is not something which is in Almgren's paper, but it's something that you should prove by reading Almgren's paper and modifying it. At least up to page 800. 800 in the 1000, not in the 1728. Once you actually modify this, you can use these ideas to prove that the interior singularities are isolated. Okay, so what I can actually do with Emanuele Spadaro and Lucas Polaur well, maybe it's maybe more 2016. So we can actually provide the starting point of his proof. So we can really prove what he needs to start his argument. And so then this has become a completely rigorous theorem. Okay, so I will explain you in a second why you should expect actually that the interior singularities are isolated in the two-dimensional case. Okay? But, so once you have actually seen this theorem, you would start simply conjecturing that at the boundary something similar is happening. So you have isolated singularities at the boundary. Now, how do the singularities at the boundary look like? Well, okay, so essentially one possible example of a singularity is I take z squared equal w to the power 3, and I take a C infinity curve which is passing through the branching. That is not difficult to pick up. Okay? That is a boundary which is going to take a portion of that surface over there, and it will have a branching at the boundary. So that branching point would be a singularity at the boundary. Now, you would expect naively that if you have this theorem in the interior, you might have this theorem at the boundary as well. And as you see, we are very far because we can only tell you that the singular point is a meager set. And here I would just tell you that the singular point is a bunch of points. Okay? So this theorem is false, actually. So we have an example. So there exists a C infinity curve gamma in R4 with countably many, I mean a C infinity, of course, closed curve, so compact with countably many singularities, or with countably many boundary singularities. Okay? So certainly the same theorem is not possible. And in some baby case, to which this theorem is also a counterexample, the approach to the interior singularity theorem would really give you that the singularities are isolated. Okay? Even though, I mean, somehow Chang's proof, so in a sense, Almgren's proof is giving you this isolatedness of singularities in the two-dimensional case for some special examples. And if you would be able to run his proof at the boundary, you would contradict this counterexample. So the proof at the boundary has to have substantial differences to the proof in the interior, although we are kind of using similar techniques.
Do you have a counterexample with real analytic curves?
No, I was about to get there. No. With real analytic curves, we actually think it's correct. And we have some toy problems for which, in the real analytic case, we can actually prove the singularities are isolated. Yes. But we are far from being able to upgrade that to a theorem for the actual problem. Yeah. Okay, so let me come to the interesting PDE computations for, well, okay, so it's the last 5 minutes, so for my PDE colleagues. So let me give you a toy problem which is a kind of very distant relative of the regularity problem. Okay, so assume you don't know anything. I mean, you don't know any complex analysis, for instance. But okay, you have these objects and you have these branching points. So one of the questions that you could ask is, I have that example with a branch isolated singularity. Okay? I can construct, of course, another algebraic variety with another branching point at some other point. Right? So why can't I construct a sequence of branching points which is converging somewhere? Okay, so one way you could actually approach this problem, which is kind of similar, is why can't I construct a holomorphic function which has a sequence of zeros which is converging somewhere? And of course, the first answer that you could give me is, well, the holomorphic function has a Taylor expansion, which is non-trivial. At the convergence point, the Taylor expansion will tell you that actually that point has to be an isolated zero. Okay? So now, using complex analysis is cheating. I mean, like, it's cheating in the following sense. So it's certainly true that there is a huge analogy between area minimizing currents and harmonic functions. But then as holomorphic functions are just a special example of harmonic functions, holomorphic subvarieties stays to general area minimizing currents as holomorphic functions stays to general harmonic functions. Maybe in the two-dimensional case, you can try to do a lot of things, but as soon as you go higher up in the dimensions, it's dead. So let me just ask the following question. So this is a sort of simple exercise. So you have an harmonic function, Laplacian of u is equal to 0, and instead of having a point which is an accumulation points of zeros, let me just assume that you have a point where the harmonic function vanishes at infinite order in the interior. Okay, then if omega is connected, the harmonic function vanishes identically. Again, that's a simple exercise. If U is harmonic, U is real analytic. If U is real analytic, it has a Taylor expansion. If it has a Taylor expansion, the Taylor expansion has to be identically equal to 0. The harmonic function is identically equal to 0 in the neighborhood of 0, and then connectedness does it. Okay? So, but if you didn't know that, so how could you prove it? There are, of course, several ways you could prove it. I mean, there's like Kahneman estimates, and the literature is plenty of this stuff. But Almgren came up with a fantastic, slick proof of this, which looks like a, I don't know, something that should have been known in the 19th century, but that apparently until him it was not known. So consider the following function, which is called Almgren frequency function. Okay, it's a calculus exercise that this function is actually monotonically increasing because of harmonicity. And this is the fantastic discovery of Almgren. So the limit as r goes to 0 of this function always exists. And the other thing that you can actually observe, and this is the other beautiful observation, the limit of this function is the degree of the first non-trivial harmonic polynomial in the Taylor expansion of your function at 0. So the fact that this guy is finite by an elementary argument tells you that you can kind of rescale the function anisotropically and find a limiting function which is homogeneous, and this limiting function is your first non-trivial polynomial in the Taylor expansion. Now, why is this for a PDE guy very exciting? Because the monotonicity of this would be valid even if I replace the Laplace equation with an equation which has kind of sufficiently smooth coefficients, like, I don't know, C2 something, without having C infinity coefficients. And of course, solutions of those equations will not be real analytic, will not be C infinity even, but the monotonicity of this guy will tell you that there will be a first non-trivial expansion in the Taylor polynomial, although you cannot write the Taylor polynomial as to start with, okay, which is a great thing. Okay, so now let me tell you an interesting computation which actually comes out of our paper. And this was kind of our toy problem as a starting point. So at the beginning we had a very messy proof of this. And then we came out with a very slick proof. And the slick proof is kind of cute. So say that I give you the same thing at the boundary. And now I give you that 0 belongs to the boundary, and the function vanishes at infinite order at that point. Then again, U is identically equal to 0 on omega if omega is connected. And again, you could use boundary regularity. Well, if the boundary of omega is not that smooth, actually, you can't really use boundary regularity that much. But you could use reflection principles and all sorts of stuff to handle this from a PDE point of view. But what would be actually the analog of Almgren's computation? Well, the analog of Almgren's computation is the following. So first of all, you have a proposition that in the interior, the following family of frequency functions are actually monotone. Sorry, I'm going extra time, but it's going to be really fast now. Okay, so in the interior, this is monotone and does the same job as the frequency function, where I have to tell you what this distance function here is. Distance function is something which looks like modulus of x plus higher order terms. I can be precise on these higher order terms. Essentially, the asymptotic of d, the first derivative and the second derivative, has to be the asymptotic of modulus of x, first derivative and second derivatives. So here I can allow, for instance, modulus of x to the power 3/2. Okay? And phi is a smooth, compactly supported cutoff function with phi prime less or equal than 0. So you recover actually Almgren's frequency function if you put modulus of x as d of x, and if you put as a cutoff function phi the indicator function of 0, 1. Okay, so then you really get a kind of, so Almgren's frequency function is a kind of singular example in a family of more regular guys. And the other lemma that you need is if omega, or if sort of the gradient of d is parallel to the boundary of omega, then that particular frequency function is monotone also at the boundary. But differently from the interior, you've got to pick up something which is really tangent to the boundary. Otherwise, the statement is false. And that actually, in a sense, is what makes, I mean, if you want, from a pure PDE analysis point of view, it accounts for the more difficulty that you have at the boundary compared as to the interior, okay, in a kind of toy situation. Okay, that's it. Sorry for going extra time.
I think this is also this is related to three balls theorem, right?
Yes.
So
yes. Yes.
Kalman estimates.
Yes. Yes. I mean, the three concepts are related. So I'm not an expert on how these things actually do relate in kind of classical PDE theory. But what I know is, for instance, that people have reproved using the frequency function what had been previously used by Kahneman estimates and three balls inequalities, which is, though, I think, a bit more special in the kind of two-dimensional setting, in the higher dimensional setting. But that's absolutely correct. And in fact, when I said that there is a portion of Almgren's work which actually was used a lot in the literature, so which came through, is precisely the PDE applications of this frequency function, which, for instance, you could use also in parabolic problems or in all sorts of other situations.
Further questions? Let's thank you.